Today we're going to look at a project I worked on about 2 years ago, a magnetless axial flux generator. This generator was designed specifically for a vertical axis wind turbine. Here's the turbine model being tested in a lab placed in front of a DIY wind tunnel using 4 high-power fans. The original setup used a low-cost, Chinese-manufactured axial flux coreless motor, which introduced unwanted friction between the rotor and stator, so this model clearly needed a serious upgrade. I redesigned the stator from scratch, 3D printed and hand-wound with wave-pattern coils. Here you can see the stator assembled alongside the rotor. To validate the design, I spun the rotor using a hand drill and measured the output on a CRO. The waveforms and peak voltages matched the calculated values almost perfectly. Even spinning it by hand, you can see how quickly the signal responds on the oscilloscope. With the modified generator installed, the turbine performed significantly better than before, but there was still a lot of room for improvement, which is why this became my master's project. And yes, this was the moment the core idea for a magnetless axial flux generator finally clicked. I began with ANSYS MotorCAD, building the initial electromagnetic model. This gave the first go or no-go confirmation that the concept would actually work. The stator was then designed in SolidWorks, using segmented ferrite cut cores instead of a single solid piece. Here's a close-up of the brushes used to power the rotor's electromagnetic poles. They're positioned close to the shaft and inside the stator, keeping the entire assembly extremely compact. The stator uses a distributed winding pattern, allowing it to be both power-dense and compact. Next, the rotor design, shown here rotating in SolidWorks from all angles. This includes the rotor backplate, the individual electromagnetic poles, the coil windings on each pole, and the central bearing assembly. Here's the complete assembly. At the cross-section, you can clearly see how tightly integrated everything is. As the rotor spins, power is transferred to the electromagnetic slip rings highlighted here. The generator and the eddy current braking system both share a common shaft, resulting in a very compact design. Smart cutouts at the top and bottom allow wiring to be routed cleanly after assembly, without lifting the generator. These slots also let the unit sit flat on the surface. With the design finalized, it was time to move from software to reality. Now let's jump to the main project and build it. Each laminated core is fixed into a slot on a plastic ring with soft plastic edges to protect the copper windings. Hundreds of parts come together to form just one stator. The stator was built phase by phase, winding each coil consistently, then wiring all 3 phases into a star configuration. This magnetic simulation shows how the 2 rotors align perfectly with the stator laminations. The CAD assembly shows precise rotor-stator alignment, with extruded teeth on each rotor pole channeling magnetic flux into the laminated cores. Here's the shaft assembly, which carries the plastic cover, slip rings, and mounts directly onto the generator. This was an early concept, a mercury-based slip ring, to eliminate sparking and brush losses, but it wasn't practical to implement. The final rotor pole design uses individual bobbins wound with copper coils. For comparison, this is the flux path in the old generator, significantly improved in the new design. The shaft assembly came together first, followed by the plastic casing. The slip ring assembly was built in parallel and then mounted onto the shaft. Now let's assemble the rotor. These are the 3D printed components used for the rotor assembly. Each rotor bobbin was hand wound, one by one. 1 bobbin, then 3, then several more, a process that took a lot of patience. Due to manufacturing costs, the rotor poles were printed using magnetic PLA instead of mild steel. The results were surprisingly good, as you can see from how strongly a magnet sticks to it. Each wound bobbin is pressed into place with its corresponding rotor pole using a bench vise. Here's the assembled bobbin and pole shown from all sides. A mild steel backplate is then slid into the rotor slot to complete the magnetic circuit. 1 pole, then 6, and finally all 12 poles installed and ready. 2 identical rotors were built for this project, which means hand winding 24 bobbins in total. At this point, the hardest work is done and the assembly starts coming together quickly. And here's the completed magnetless axial flux generator. It spins freely with just 1 finger, showing how smooth and well-balanced the build is. On top sits an eddy current braking system, a side project that deserves a video of its own. Here's the brake fully assembled and ready to be mounted above the generator. This combined assembly acts as a generator, brake, and stable base. The turbine mounts directly on top, sharing the same shaft. A comparison between the old setup and the new, cleaner, more compact assembly. This is the generator output measured on the CRO. Further performance details are classified. If you enjoyed this project, subscribe to the channel, like the video, and share it. More deep dive engineering projects coming soon.